Okay, in section 2 is called What Derivatives Tell Us, and this section is huge in terms of the amount of content that is inside of it. Now, a lot of it can be just summed up with the two theorems that I have here. Theorem 4.8, the first derivative test, and then Theorem 4.11, which is the second derivative test for local extrema. And these tests, honestly, they kind of go by different names, really. The first derivative test, it'll tell us intervals of increasing and decreasing. And then the second derivative test will tell us concavity and points of inflection. And then at the very end of this, once I'm done doing my examples and everything, I have this table right here, which is just a summary of everything that section 2 basically tells us. So let's go back up to the top and let's look at this right here. So we're going to look at the first derivative test, and then I'm going to do some examples of this. Now, the first derivative test tells us intervals of increasing and decreasing. Now, the way that we go about finding these intervals is that we are going to find the first derivative, set it equal to 0, and find those critical values again. So let's go ahead, let's read the theorem, and let's see how we can use that to our advantage. So assume f is continuous on an interval that contains a critical point c, and assume f is differentiable on an interval containing c, except perhaps at c itself. If the derivative changes signs from positive to negative as x increases through c, then x has a local max at c. So what they're saying is the slopes of the tangent lines go from positive, then to negative. You have a local max. And if you think about this, if I were just to kind of just connect these two arrows I just drew and make it nice, smooth, and continuous, notice you have a max. Now for the second bullet point, if the derivative changes signs from negative to positive as x increases through c, then you have a local min. So remember, this is saying negative to positive. And if I were to connect those, notice you got a local min. And then the third bullet point is if f is positive on both sides near c, or both sides, or negative on both sides near c, then f has no local extreme value at c. Okay, so if they're both positive at c, it looks something like this. Notice it just goes over like that. Or negative, it comes down like this. Okay? Excuse me. So let's look at some examples of that. So we're going to go here, and we're going to do some examples of the first derivative test. Now, whenever you see the words first derivative test, what you're really thinking is, and the directions will actually say it, find the intervals on which f is increasing, let's say is either increasing or decreasing. And this is very, very simple, okay? So the first example, we're going to keep it nice and neat for now. We'll do f of x equals x squared minus 16. Now, to find these intervals, you need to find a critical point, or the critical value. And that critical value is going to be when the derivative equals 0. So first, let's find the derivative. So f prime of x is going to equal 2x. Now we set this equal to 0 and solve for x. So I know when x equals 0, I'm going to have either a min, slash, or a max. Like, I know that's going to happen. So how we do this is, off to the right, we just create a number line. That's it. And we're going to use, let me highlight this here. We're going to use this equation right here, our derivative equation, to determine the slopes of the tangent lines. Because remember, the slopes of the tangent lines tells me if this is increasing or decreasing. So if I were to choose a value in the interval of a, now the interval a is going to be negative infinity all the way up to 0. You cannot include 0 because at 0 we have a horizontal tangent line. So if you choose a value in interval A, let's say -10, and you substitute -10 in for x in our derivative equation, notice you get -20. So in other words, all of the values in region A from -infinity all the way up to 0 will always make this negative. All the way up to 0. At 0, we have a horizontal tangent line, so f prime of 0 equals 0. We know that. And now what we're going to do is we're going to choose a value on the right-hand side. So this is going to be region B, and that interval is from 0 to infinity. So when we go ahead and choose a value, let's say x equals 10, and we substitute that into our derivative, we get 2 times 10, which is positive 20. But I'm going to be honest, I don't care what the number is. All I care about is what's the sign of that number, and that sign is going to be positive. So according to the first derivative test, at 0, we have a local min because it goes from negative to positive. So it goes just like that. And the intervals, which is what they're asking us for, they're intervals of increasing. Well, it increases from 0 to infinity and decreases from -infinity to 0. And if you can just buy into that basic concept right there, all of this becomes very simple. Remember, mathematics is not about memorizing problems. It's about understanding techniques. It's about understanding theorems or definitions. And that first derivative test tells us intervals of increasing and decreasing. All right? Now, excuse me, let's do another example here. So we'll do another example that's a little bit more involved. So f of x equals x to the 4th minus 4x cubed plus 4x squared. So once again, we're going to find the intervals of increasing and decreasing. To do that, let's find our derivative. So it's going to be 4x cubed minus 12x squared plus 8x. We're going to set this equal to 0. And because this is a cubic function, I'm going to try to factor it first, see if I can make this a little bit easier on myself. So I notice that I do have a GCF of 4x. So when I factor the 4x out, I'm going to get x squared minus 3x plus 2. Now I can hopefully factor the trinomial inside the parentheses. So write an x and an x. I always copy down the first sign. The second sign has to be negative because those last two numbers that I multiply are going to be a positive number. And since they're both negative, the factors of 2 are 1 and 2, and they both combine to give me -3. So now I set each one of these factors that contains a variable equal to 0. And when I solve, I've found those critical values for my number line. Now, give me 1 second here because I want to leave it just like this. All right, so we have 0, 1, and 2. Perfect. So if you look here, I have 3 regions. No, I'm sorry, 4. I have region A, B, C, and D. And I'm going to go underneath, and I'm going to label every single one of those, okay? So this is going to be -infinity to 0. This is going to be 0 to 1. This will be 1 to 2. And this is going to be 2 to infinity. Now, I'm concerned with increasing or decreasing, and the derivative is going to tell me. Therefore, I'm going to use the factored form of my derivative. So that's going to be right there. I'm going to highlight it in green so you all know what I mean. Did that rhyme? Did that rhyme? I think it did. I'm pretty cool then, I guess. I don't know. So here we go. Now, you really gotta listen to what I'm saying here. We're not concerned with the number. What we're concerned with is what's the sign. The sign will tell me increasing or decreasing. So, if you take a number out of region A, all right? So, I'm looking for a number in the interval of negative infinity all the way up to 0. And I'm going to choose one that's just pretty simple to do. So I'm going to choose -1. Now, what I do is I come up into my derivative, and I'm going to substitute in a -1. And I'm only going to do this once or twice just to show you. All right, so let me just draw like a little line there. There you go. What I'm concerned with is, excuse me, signs. I know 4 times -1 is a negative number. I know -1 minus 1 is -2, but I'm not concerned with a number. It's negative. And lastly, -1 minus 2 is -3, but once again, I just want the sign. So it's a negative. And if you now, or maybe now you can see why I want the factored form. When I factor something, all of those factors are being multiplied. So a negative times a negative is a positive, and a positive times a negative is another negative. So I know in region A, the signs of all of my tangent lines are going to be negative. Like I know that. And I know that because my derivative told me so. So now we're going to go in between 0 and 1. So I'm going to erase all this red stuff that I just wrote. Okay? And we're going to choose a value of x in between 0 and 1. So let's just say 1/2. So I'm going to write 1/2 here for now. Okay? So 4 times 1/2 is 2, but it's positive. 1/2 minus 1 is negative. And 1/2 minus 2 is still negative. So I have a positive times a negative, which is a negative. And a negative times a negative is a positive value. So the slopes of all my tangent lines in between 0 and 1 are all positive. Now we're going to do the same thing. We're going to pick a value in between 1 and 2. So that value, let's just say it's 3/2 or 1.5, okay? So 4 times 1.5 is still a positive number. Oops, sorry. So it's still positive. Now, 1.5 minus 1 is 0.5, which is still positive. However, 1.5 minus 2 is -0.5, which is still negative. So my derivative will be negative. So in between 1 and 2 in region C, they're all negative. And just to exaggerate my point, in region D, I'm going to choose the value 100 because that is definitely in 2 to infinity. 4 times 100 is 400. It's positive. 100 minus 1 is 99. It's still positive. 100 minus 2 is 98, which is still positive. So all of my slopes of the tangent lines in region D are positive. So to answer the question, where are the intervals increasing? Well, the intervals are increasing from 0 to 1 or 2 to infinity, and they are decreasing from -infinity to 0 or 1 to 2. And that's it. That's how that's what the first derivative test tells us. It lets us know first where there's critical values, where I'm going to have horizontal tangent lines, but more importantly, it gives me the idea of increasing intervals and decreasing intervals. In fact, if you went to Desmos, so give me a second here. Let me pull up Desmos. See if I can kind of do this. We'll shrink this down a little bit. There we go. We're going to try to do this as best as we can. Y equals, and I'm going to go ahead and type in the original function, which was x to the fourth. I can't see it. There it is. X to the fourth minus 4x cubed. Oh, can't type right now. Minus 4x cubed plus 4x squared. All right. So just give me a little sec here, because what I'm going to do is I'm going to copy this and paste it. So you know what I should do is just maximize this. We're going to make it look really nice. Boy, I love when things just work out nicely, don't you? Now we need the numbers. I don't want the minor grid lines. There we go. We'll use this snip feature. All right, there we go. Perfect. Look at that. I love it. Okay, we don't need that. Uh-oh, I hear a dog barking. My dog's probably going to bark. We'll zoom in just enough so we can see the intervals. And here we go. So we got an interval from negative infinity all the way up to 0. That's going to be right here. So I'll just draw a line. We'll break up that. Notice all the slopes of my tangent lines are negative. So from negative infinity to 0, they're all negative, which is exactly what we just said. So this right here would be region A. Now, in between 0 and 1, all the slopes of my tangent lines are all going upward. Let me draw tangent lines. They're all going up. There's region B. Now, from 1 to 2, they're all negative again. And then from 2 to infinity, so I'll just write it off to the side here to the right. They're all positive again. So, I'll be honest with you, it wouldn't hurt to graph this stuff. It really wouldn't. But the thing is, you got to know how to find these derivatives, because sometimes when you graph them, they're not really pretty. And that's where calculus kicks in. That's where it really helps you to know how to graph them, so you can easily just figure out just what are the slopes. And remember, when we're talking slopes, you need to be thinking, use the derivative equation. I've seen too many students, they understand what to do, meaning, take the derivative, set it equal to 0, find the critical values. They get that. But then they substitute it into the wrong equation. Remember, when you're trying to find points, use the original f of x. Because remember, f of x is like really fancy, cursive writing for the letter y, okay? When you're trying to find slopes of tangent lines, you need to be thinking derivative. Therefore, and I'm going to use a different color here to highlight it, you need to be thinking, oh, that looks terrible. Why don't I just circle it in a different color? You need to be thinking derivatives, okay? Points, original function. Slopes of tangent lines, derivatives. All right? So now that we have those two kind of done, let's look at the next definition here. So the next definition deals with our second derivative test. And another way to kind of describe that is concavity or points of inflection. So suppose the second derivative is continuous on an open interval containing c with the derivative of c, the first derivative of c equal to 0. If the second derivative is greater than 0, then f has a local minimum at c. If the second derivative is less than 0, then f has a local maximum at c. And then if the second derivative equals 0, then this test is inconclusive, meaning that you may have a local max or a local min, or neither at c. So this picture that I have here on the screen is actually in your book. It's the very last page in section 2, or section 3, I'm sorry. And it summarizes everything that we need to know in this chapter, or in this section. So what I want us to look at here, and I'm going to put stars. I want us to look here, here, and here. So I guess I could have just summed that up with the last row. So the last row basically says this: if your second derivative, you know what? I'll zoom in a little bit more. If your second derivative is greater than 0, then we say f is concave up on that interval. Now, if you think of concave up, this is going to sound really dumb, but concave up rhymes with cup, and it forms a cup. So we can have this, or we can have this. The key is that the slopes of all of your tangent lines will lie underneath the curve. So they all lie underneath the curve. All right, no matter which way you look at this, they always lie underneath the curve. Okay? Now, if we look at the second picture, if the second derivative is less than 0, in other words, if it's negative on an open interval, then we say f is concave down. And once again, I think like a 5-year-old sometimes, concave down rhymes with frown. So if you notice, this is making a frown right here. So if I just connect them, it's making a frown. But more importantly, when we go ahead and graph our tangent lines, they lie above the function. All right, they lie above the function. Because remember, a tangent line only touches your function once. You cannot do a tangent line underneath. You can't do it because you would end up hitting it twice. So all of your tangent lines lie above the function. So concave up rhymes with cup. It looks like a cup. Concave down rhymes with frown. It looks like a frown. Now the last picture, if your second derivative changes signs, you have what we call an inflection point. Now, I went over inflection points, I think back in like chapter 1 or chapter 2. I can't remember. But I did say inflection points is going to be a point at which your derivatives, or better yet, the slopes of your tangents change from positive to negative or negative to positive. It doesn't matter what they're doing, is they're changing from one sign to the other sign. And that is going to occur when your second derivative evaluated at c equals 0. In other words, you're going to find what is that critical value when you take the second derivative. That is the point of inflection. Okay? And you can see, since they give you this example here, all of your slopes of your tangent lines are positive, which means concave up. But then at this point, they change to negative, which is concave down. All right, so if I just zoom out here a little bit and just erase all this nonsense I have, now you can start to piece the two pieces of information together. So remember, first derivative tells us intervals of increasing and decreasing. Second derivative, I'll scroll up, tells me concavity and points of inflection. So let's go ahead and let's look at a couple examples using that, okay? Excuse me. So directions are very simple. What we're going to do, let me get out a black marker here. Here we go. We're going to locate the critical values or the critical points. And then use the second derivative to determine concavity and points of inflection. Now, another way I've seen the directions in other books. They might say something like this, like verify max / min values, which what they're asking for once again is concavity. They want to make sure, okay, your intervals show that yes, this could be this could be a max or a min, but in reality they want you to verify it, and the way to verify it is with concavity. Okay, so like I said, this one we'll start off with a pretty easy example, and then we'll get a little bit more difficult. So here's our first example right here. This is going to be f of x equals x to the third minus 3x squared. And I'm going to do this one a little differently. Normally what I would do is walk you through it and everything and then show you the graph. I'm going to show you the graph first, because I think by showing the graph first, we already know what the answers should be. I'm going to demonstrate, okay, let's make sure we're correct now. So y equals x to the third minus 3x squared. Let me just zoom out here a little bit. All right, that looks pretty good to me. We'll change the color. We'll make it black. Click on a couple points right there. It's pretty nice. And then I'm just going to copy and paste this into our notes. All right, that looks beautiful. All right, so real quick, here's what we know. Critical points. X equals 0, x equals 2. Why? Because I have horizontal tangent lines at those x values, okay? Second, intervals of increasing / decreasing. Well, since I have my critical points at 0 and 2, I'm looking at slopes of my tangent lines. So the slopes of my tangent lines, if you look at the graph right now, in this interval, they're all positive. So I guess maybe I should just write some plus signs. So they're all positive. That's the interval from negative infinity all the way up to 0. The second interval is in between 0 and 2, and they're all negative. And then the last interval is going to be from 2 to infinity. 2 to infinity and beyond. How many times have you said that in your head when you're doing calculus? So these are all positive. All right. So, I mean, just by looking at the graph, there's so much information here for us. Okay. Now, we're even going to go ahead. I'm going to erase this real quick. No, actually, I should have left that there. The power of technology. I can just hit Control-Z on my keyboard twice. So now this right here, everything I found was all the first derivative test. Okay. Now in red, and I'm going to make sure this red marker is real thick. In red, here comes the second derivative test. Now, we didn't do any test yet, but we can see what's happening. Notice from here all the way to about here, all the slopes of my tangent lines are going to be above. Be above my function. That to me looks like a frown. So from, and we're gonna estimate this, okay? So from let me see, this looks like it's about 1. So from negative infinity, boy, it'd be nice if I wrote negative. So from negative infinity to 1, we have concave down. Because remember, it looks like a frown, concave down. Now, in a different color, what color don't I use? Let's use green. And we'll make sure it's nice and thick. So from green, so from this point here, and I'll make it half green, half red. So from here all the way up. So that looks like this is the interval from 1 to positive infinity. That looks like a cup, concave up. And now I'm going to use blue to marry those two colors together. That is going to be my point of inflection, which right now, I'm estimating this. I'm estimating. It looks like it's about 1. So when I go ahead and do these tests here, okay, when I do these tests, if I come up with 1 or a number really, really close to 1, I'm going to feel really good about myself. So off to the right here in black, I'm just going to write second derivative test. Looking at what we have, we should come up with everything that I have outlined here. So the second derivative, obviously, goes without saying, we need the second derivative. So the first derivative is going to be 3x squared minus 6x. My second derivative, is going to be 6x minus 6. Now, when I set that equal to 0 and solve, this gives me my point of inflection, or POI, point of inflection. I'm going to zoom out just a little bit here because I'm going to add 6 to both sides. 6 equals 6x. Divide both sides by 6. Holy cannoli. We get x equals 1. Fantastic. All right? You don't understand. You can't see my face right now, but I have a huge smile on my face. I'm so excited. Now, I found my point of inflection. This is also a critical value for concavity. Meaning, watch this. I'm going to draw a line. I'm going to put a 1. Actually, you know what? Let me do this even better. There we go. Look at that. I'm going to draw a number line. I'm going to label my point of inflection, which is 1. Now, I'm going to take this second derivative right here. Let me highlight it for you so you know exactly where I'm looking. I'm looking right here where I just highlighted that in blue. I'm looking there, and I'm trying to determine in the first interval from, you guessed it, negative infinity to 1, what are the slopes of my second derivative? And that will tell me, that will guarantee me concavity. So if I look at the slopes here, okay, excuse me, I take a number inside that interval. Why don't we just use 0? That's in that interval. So f double prime of 0 is going to equal negative 6. Notice this is negative, okay? And remember, let me go back. Sorry, I'm jumping all over the place. I'm really sorry for this. If your second derivative is less than 0 or negative, concave down makes a frown. And when you look at what we have here, we definitely have that. So this is concave down. Now, from 1 to infinity, hopefully we get positive values. So 1 to infinity, let's say the second derivative we evaluated at 10. Well, that's going to give me 60 minus 6. I really don't care what the number is because I know it's positive. And if I go back to our second derivative right here, if your second derivative is positive, you have concave up. Or the picture makes it look like a cup. And this, to me, in green, definitely looks like a cup. So concave up. And that's it. That's what the derivative tells us. This derivative is so unbelievably important because it really gives me 3 pieces of information. It gives me horizontal tangent lines. It gives me intervals of increasing and decreasing. it gives me concavity / points of inflection. And just by knowing those three things, I can take any function and quickly graph it with really good accuracy just based off of those three things. So let's go ahead. Let's do another example. Now that we understand how this works, I change my marker to a black marker again. Let me zoom in some. All right, so here we go. So here's another example. Let's look at f of x equals e to the x times the quantity x minus 2 squared. Okay, so we're asked to find concavity, points of inflection. All right, so let's go ahead. Let's do this one. Now, our first derivative, and I'm just going to tell you what the derivative is. That way this video isn't, 40 minutes long. And also, what you can do is you can go ahead and take the derivative yourself and then see if you come up with the same exact thing that I did. So our first derivative is going to be x, the quantity x plus 1 e to the x. Oh, sorry. I'm looking at the wrong notes here. I am looking at the wrong notes. My bad. So our first derivative is going to be e to the x times x minus 2 quantity squared plus e to the x times, you got to do the chain rule on this one. So it's going to be x minus 2 times 2. We can clean that up a little bit. E to the x times x minus 2 quantity squared plus 2 e to the x times x minus 2. And the second derivative is going to be a little bit more involved. So the second derivative is going to be, and I'm just going to give you the simplified version. E to the x times the quantity x squared minus 2. So let's see if you can come up with that. Now, just to give you a hint, product rule all over again. And then you're going to group all your like terms. Okay? But if you do it correctly, you should come up with this. All right? Now, to find concavity and points of inflection, we set this equal to 0. We set each variable that contains an x equal to 0. Now, e to the x will never equal 0. So you don't have to worry about that one. But we do have x minus 2, or x squared minus 2 equals 0, which means x squared equals positive 2. And then last but not least, you get x equals plus or minus the square root of 2. Remember, everyone, when you take the square root of both sides, you have to put the plus or minus there. Okay, a lot of students forget about the plus or minus. Please don't forget about the plus or minus, all right? So we got a number line, negative square root of 2, positive square root of 2. All we're really concerned with, though, is the second derivative. And what's really nice is we have up above, I'll highlight it in blue for you, our second derivative is already factored. That is so nice for us, okay? Because what we can do is just figure out signs. So notice we have 3 intervals. So let me just label the intervals here. We have the interval from negative infinity all the way up to negative square root of 2. We have the interval negative square root of 2, to positive square root of 2, and then the interval square root of 2 to positive infinity. Okay? So let's take our factored form. Second derivative equals e to the x times x squared minus 2. And let's figure this out. So a number from negative infinity to negative square root of 2, I'm just going to use negative 10. So my second derivative evaluated at negative 10 is going to be e to the negative 10 times negative 10 squared minus 2. Here's what we know. that is never below 0. It's never negative. All right, so we don't have to worry about that. Negative 10 quantity squared is positive 100. So this is going to be a positive times a positive, which is a positive. So this is all positive right here. All right. Now, convince yourself that e to the negative 10 is not negative. Remember, e to the negative 10 is 1 over e to the 10th. It's a positive number. Okay? Next. A number in between square root of 2, or negative square root of 2 and positive square root of 2. How about 0? E to the 0 is 1. 0 squared minus 2 is negative 2. Regardless, these are all negative. Lastly, a number in the interval from square root of 2 to positive infinity. Well, once again, you can, if you want to, you can get crazy with it. Make it 100. E to the 100 is an extremely large positive value. 100 squared is an extremely large number minus 2, but it's still positive. And a positive times a positive is another positive. Now remember, these two values right here, negative square root of 2 and positive square root of 2, points of inflection. All right? If your second derivative is positive, we'll go back to the notes real quick. Second derivative is positive, concave up. Second derivative is negative, concave down. So, in this first region, I'm expecting concave up. In the second region, I'm expecting concave down. In the third region, I'm expecting concave up. So, if I were to graph this, I would expect something that looks like this. Concave up, we know makes a cup. Concave down makes a frown. Concave up makes a cup. So I'm expecting something that has this flow right here. So let's go ahead and just graph it using Desmos. So with Desmos, let's see here we got, what was I don't remember what it was. E to the x, so y equals e to the x times the quantity x minus 2 squared. All right, now the square root of 2 is approximately 1.4. So negative 1.4 and positive 1.4. So all I'm going to do is just kind of gauge where this is. So let's see here. Oh, come on, work with me. There you go. So notice, right there's your point of inflection. Now, if we really wanted to find a point of inflection, what we would have to do is take negative square root of 2 and substitute it into our original equation to find the point. But it's going to be the point negative 1.4, comma 2.8, something like that. Ow! My cat just scratched me really bad. Sorry about that. You guys are probably laughing on the video. I'm laughing right now. So that's what this is approximately. Then also notice it forms a cup, sort of. So from negative infinity all the way up to negative 1.41, all right, it forms a cup. Then in between negative square root of 2 and positive square root of 2, which is going to be over here. So 1.41, let's try to find it. So right about here, all right, notice you got that frown, and then afterwards, it forms a cup again. So it's exactly what we expected it to be, which is fantastic. And if you think about it, if I were to ask you, just off the top of your head, what do you think e to the x times the quantity x minus 2 squared looks like? I don't know if a lot of us would come up with what we have right here. I mean, honestly, I would think a lot of us would say, well, it got to have a parabola in it. And the reason why you would say a parabola is right here. The quantity x minus 2 squared, well, that's x squared if you forget about the minus 2. That's a parabola. We know that. All right, we're cool with that. But that e to the x kind of changes things a little bit, all right? So that's it for this section right here. I hope this made a lot of sense. For me personally, everything can be summed up right here in this table. So we're going to look at this table just one last time. So first, in the upper left-hand corner, so let me show you where I'm looking, where the red star is. First, you have f is differentiable on an interval, and f is a smooth curve. Now, if we have that, as we go from left to right, top to bottom, all this starts to apply. The first derivative, if it's greater than 0, increasing interval. If the first derivative is less than 0, decreasing interval. If your derivative changes signs from positive to negative or negative to positive, you know you have either a local max or a local min. Now, if the first derivative equals 0, here's my cat again. If the first derivative equals 0 and your second derivative is less than 0, you are guaranteed to have a local max. If your first derivative is, and let me highlight here because I think I'm moving a little fast here. So if your first derivative equals 0 and the second derivative is less than 0, you have a local max. Next, if your first derivative equals 0 and your second derivative is greater than 0, you have a local min. And how do you know that? Because if your second derivative is greater than 0 on the open interval, you have concave up, makes a cup. And if your second derivative is less than 0 on an open interval, meaning it's negative, you have concave down, and it makes a frown. Lastly, your second derivative, if it changes signs, you know you got an inflection point. And the only way you're going to know any of this is by go ahead, finding these points of inflection, finding the first and second derivative, labeling the points, all right? Labeling on a number line, and then using either the first or second derivative to find out what are the signs of those tangent lines on those intervals. And that's it. So the key here is to take the derivative, set it equal to 0, go ahead, do a number line. Then, second derivative, set it equal to 0, do a number line. Whatever those signs are will tell you everything that you need to know. I hope this video was informative, and I'll see you in the next one. Bye.